So we have been doing a new method called MRept, or magnetic resonance electrical properties tomography, and we have been using that to measure intrinsic tissue conductivity. So you can use the phase image that you acquire with MRept to generate a quantitative map of the tissue conductivity in the brain, and that will allow you to non-invasively, I think, look at brain activity and different cell constituents in the brain. And in our hands we have been acquiring very repeatable maps. So our repeatability is around 4% when we redo the map, which I think is better than previously published values, which are around 10%. And we've also found that using compressed sense we can speed the acquisition up. So it's now at the point where it could be used reliably in the clinic, so very quickly. We have a 3.5 minute scan, but you could get away with a 2-minute scan, or maybe even a 1-minute scan, depending on how accurate you need to be or how precise you need to be. I think the contributors to the repeatability of the study are things like the stability of the RF. So the system gives pretty much the same sequences and the same pulses every time. So if we repeat the image, we get the same data. The integrity of the gradients, the linearity of the gradients goes to that. So if you repeat the image over and over, you get very much the same answer, which is really reassuring for the scientist. The conductivity imaging is made easier by having a very good balanced fast field echo sequence, for example, which is the main one that we're using. You can also do this with the turbo spin echo. The turbo spin echo has probably less phase artifact in it, but we've managed with the BFFE to reduce the artifact to the point where it's almost minimal. And again, that is because the system generates very, very nice phase maps for us. People have started to use tissue conductivity imaging for detection of tumours and cancerous growths, and it picks up tissue which is different to what you expect. So, you can pick up calcifications, we've picked up lipomas, we've picked up tumours like that. One of the main applications for this will be in outside the brain as well, I think. So we have been doing some prostate imaging with it. It picks up really nice changes in tissue conductivity in prostate cancer because the conductivity goes down because you've lost seminal fluid in that particular part of the tissue. So it may be useful for prostate cancer, for example, to tell the difference between inflammation and cancerous tissue, which could be useful for the radiologist. I get very excited about tissue conductivity imaging because I think it has a whole plethora of potential applications in the future. We're just starting to explore those at this point, but it's looking really, really promising. So the thing that has really got me excited about tissue conductivity imaging is, since we got our new scanner and being able to see exactly what it does with this technique, it has really got me engaged with magnetic resonance imaging again and really excited about the research that I'm doing.